Welcome to Unit 6, Inference for Categorical Data with an emphasis on proportions. In this video, we're going to be talking about topic 6.10, setting up a test for the difference of two population proportions. Just to give you a heads up, this video is going to go through all of the steps, exactly how to set up a test. And then in 6.11, we're going to actually do it. We're going to do a couple practice problems to do it. So please make sure after this video, you go ahead and move on to 6.11 to see how it's actually done. All right, comparing two proportions. One thing many research studies aim to do is to see if there is a difference between two different populations or proportions. To be quite honest, in the world of research, this is actually probably what's done most often, is we want to compare two different populations and see if there's a difference between those population proportions. So here's three examples. A teacher might wonder, hey, I think the proportion of boys that do their homework is less than the proportion of girls that do their homework. So two different populations, boys and girls, and we're looking at the proportion that do their homework, and this teacher believes that boys do less than girls. An economist might wonder, hey, I think the proportion of unemployed adults in the United States is greater than the proportion of unemployed adults in Canada. So two different populations, United States and Canada, and we're looking at the proportion of unemployed adults, and hey, economist thinks it's greater for the United States. A marine biologist might wonder, hey, I think there is a difference between the proportion of diseased coral reef in the Atlantic Ocean and the proportion of diseased coral reef in the Pacific Ocean. Not necessarily saying that one is higher than the other or that the Atlantic Ocean is lower or the Atlantic Ocean is higher. The biologist just thinks that there is in fact a difference. I mean, they're not the same. Now, let's make sure you understand that to answer these questions, we don't need a confidence interval, because remember, a confidence interval is needed when you simply don't know the difference. You don't have any idea, and you're just wondering, hey, what could the difference between these two population proportions be? That's when you use a confidence interval. Here, we have three claims, right? The teacher thinks that the proportion of boys is higher than the proportion, less than the proportion of girls. If the teacher wants to figure out if her claim is correct, she's got to put it to the test. An economist believes, in his opinion, that unemployed adults in the United States is greater than the proportion of unemployed adults in Canada. If he wants to prove he's right, he's got to do it with the test. Marine biologist believes that there is a difference between diseased coral reef in the Atlantic Ocean and the Pacific Ocean. If he wants to prove he's right or show that he's right, he needs to go ahead and do a significance test to show that. All right. So this is a concept we know, right? We've already talked about how to do a test for a one sample proportion, right? So here we're talking about a claim. A claim has been made about two population proportions. It's our job to try to show that that claim is correct, right? The teacher wants to show that she's right. Proportion of boys is greater than girls when it comes to doing homework. So it's our job to collect significant evidence in the form of samples that hopefully can prove our claim to be right. But at the same time, maybe we don't get enough evidence and therefore we cannot justify our claim. But at the end of the day, we want to show our claim is true. So we're going to try to collect evidence to show it. Maybe we do. Maybe we just don't have a whole lot of evidence and we can't do it, right? This is a whole process that should sound very, very familiar. Here are the four steps. The first step is to name the test and give the hypotheses. We're going to talk about that at length. Number two is to check the conditions necessary and build a sampling distribution for the difference. Now, the one thing you got to remember is in a test, when you build that sampling distribution, it's on the assumption that the null hypothesis is true. So we really need to understand what that null hypothesis is, which we will. The work is simply saying, okay, now I have my evidence. I got a sample of boys that did their homework. I got a sample of girls that did their homework. And I want to show that the proportion for the boys is significantly higher. So what we're going to do is we're going to look at our difference, our sample difference, and we're going to find the Z-score for our sample difference. Then we're going to find the p-value, and then we're going to make a conclusion based on that p-value. We either do have the evidence to show that our claim is correct, or we just have a lack of evidence to show our claim is correct. Therefore, we're going to fail to reject the null. So we already know this process pretty well because we've already done it. But now we're just looking at it a little bit differently. Now, I'll be honest, the large majority of these four steps is exactly the same as what we've been doing, but there's a couple small, really important changes that you need to understand. All right, so first off, let's talk about step one. Step one is naming the test and giving the hypotheses. So the name of this test is a two-sample Z test. Now, you have to throw some context there in any specific problem. For example, I'm going to do a two-sample Z test for the difference between the proportion of boys and girls that do their homework. I'm going to do a two-sample z-test for the difference between Americans and Canadians that are unemployed. I'm going to do a two-sample z-test for the difference between Atlantic and the proportion of Atlantic and Pacific coral reef that are diseased. You got to make sure that you give that name, two-sample z-test, and the context after it. All right, now let's talk about the null. The null hypothesis is really, really important to understand. And the idea is actually pretty simple. We have to believe that there is no difference, right? Just like in a court case. The jury has to believe that the potential criminal is innocent. You got to believe he's innocent. So our null is that there is no difference. Boys, nah, they're not higher than girls. They're equal. Atlantic Ocean, Pacific Ocean, nah, they're the same. Proportions are equal. America, Canada, proportion of unemployed adults, nah, they're the same. We have to assume that they're the same, right? That's our null. Now, a lot of kids look at this and they say, well, where's the number? Shouldn't there be a number there? Well, there actually kind of is a number. Let me show you where that number's at. Technically, if you have two proportions that are equal, right? What that means is that there's no difference. And if there's no difference, that means the difference is 0. So if you really truly feel that you need to see a number here, just subtract the proportion from population 2 over, and you get P1 minus P2 equals 0. So there's a number right there if you really need a number. If we truly assume that there is no difference between the proportion of population 1 and the proportion of population 2, then that means that the difference between them would be 0. So whether you say that they're equal to each other, which means they're the same, that also implies that they're equal. All right, now the alternative is our claim, what we believe to be true. The teacher believed that the proportion of guys was greater than girls. The economists believed that the proportion of Canadians was actually less than the proportion of Americans. Or the biologists believe that nobody's higher, nobody's lower, there's just a difference. So again, you actually have 3 different options for the alternative. It is that the proportion from population 1 is greater than population 2, the proportion from population 1 is less than population 2, or simply that they're not equal. Now remember, if your alternative is that they're not equal, we do call that a two-sided test, as opposed to a one-sided test. Because here we only care about 1 being greater than 2. Here we care about 1 being less than 2. Here we just don't really care who's less or who's greater. We just care that there is a difference. We call that a two-sided test. So there's actually no numbers. But again, if you really need a number, you could use a 0. But the idea is the null is saying, hey, there's no difference here. Whereas the alternative is our claim that we believe something else to be true. So let's look back at our 3 examples so we could practice writing these hypotheses. Okay, so a teacher wonders, hey, I think the proportion of boys that do their homework is less than the proportion of girls. So this is going to be a 2-sample z-test for the proportion of boys and girls that do their homework. So the null would be that, no, they're the same. The proportion of boys that do their homework is exactly equal to the proportion of girls that do their homework. And then again, the alternative is, again, this is what we're trying to show evidence. We want to prove that this is correct. We want to prove that the proportion of boys that do their homework is less than the proportion of girls that do their homework. Now, just so you know, you don't have to write it this way, right? Saying that the girls is greater than the boys is equivalent to this statement. So you could write it either way if you want. That would technically be the same thing. This next example was with the economist. And again, his null is going to be, status quo. The proportion from the U.S. is exactly equal to the proportion of unemployed adults from Canada. But then the alternative is what this economist is really hoping to show. He's really hoping to show that he is right and that the proportion of unemployed adults in the U.S. is greater than the proportion of unemployed adults in Canada. Okay? So notice that don't use 1s and 2s. That's way too generic. Obviously, we're going to use 1s and 2s in any formula, but you put some context to the problem. All right, and then finally here, the null is going to be, the proportion from the Pacific Ocean is equal to the proportion from the Atlantic Ocean. There's no difference between the proportion of diseased coral reef, where the alternative is, no, this biologist truly believes that there is a difference. He doesn't really care who's higher or who's lower. He just cares that there is, in fact, a difference. All right, now, just real quick, just to remind you, when you do have that alternative that is a not equal to, the only big difference is that at the very end, when we get to the very end, when we calculate that p-value, make sure you times it by 2. In one of our examples, we'll show you that. But that's the only big thing you need to remember with an alternative of not equal to sign. All right, so hopefully step 1, the hypotheses and naming the test is pretty easy, not overly difficult. All right, step 2 is where things get a little weird, so please pay very close attention here. All right, we have to assume the null hypothesis is true. That is by far the most important thing, right? We're assuming that the two proportions are the same. We don't know what that proportion is, that they're both equal to. We just know that those proportions are the same, right? So if I'm thinking about the boys and girls, I don't know if it's 70% that do their homework for boys and 70% for girls, or if it's 65%, 65%, or 81%, 81%. I just know that they're the same. That's my null, that they're the same, right? So I need to build a sampling distribution on that assumption. All right, so first, sorry, I know a lot of kids don't like to do the conditions, but you gotta do the conditions. Let's run through the conditions real quick. Both samples have to be random to avoid bias. The sample of girls has to be under 10% of the population of girls. The sample of boys has to be under 10% of the population of boys to assume independence. And both samples have to have 10 or more successes and failures so that the sampling distribution can be normal. Okay. When we've done those conditions enough. When we look at some exact examples in 6.11, we will see us going through those conditions. All right, but remember, when I build that sampling distribution, once the conditions have all been checked, I need to think about the mean, the center of that sampling distribution, and I need to think about the standard deviation of that sampling distribution. All right, let's talk about the center, because that's the easy part, the mean. Well, if it's really true that the two proportions are the same, then the mean of any potential difference should be 0. Because if I'm assuming that these two proportions are equal, whether they're 80%, 80%, or 70%, 70%, or 16%, 16%, that means I assume the difference to be 0. So smack dab in the middle, the mean of the sampling distribution for the difference between two samples is going to be 0. Now, please make sure you understand what a sampling distribution shows you. Could a difference be a little higher? Sure. Could a difference be a little lower? Sure. But the mean of all possible differences between two samples should be 0 if, in fact, the null is true. Okay, that's the easy part. A lot of kids have no problem with that. All right, but what about the standard deviation? Well, we run into a problem. Here is the formula for standard deviation of the difference between two samples. It is a giant square root. It's the true proportion from population 1 times the opposite divided by sample size from population 1. The true proportion for population 2 times the opposite, all divided by the sample size taken from population 2. All right, well, we run into a problem. Here's the problem. Our mean tells us that we expect these two proportions to be equal, so that's why the mean is 0. Okay, that's easy. But I don't know what these two proportions are. I just know that they're equal to each other. Are they 16% and 16%? I don't know. Are they 80% and 80%? I don't know. Are they 71% and 71%? I don't know. I know they're equal, but I don't know what they are. See, that wasn't a problem for the mean because it doesn't matter what they are. The difference is going to be 0. But when you're talking about the standard deviation, to calculate it, I need to know these individual values, and I don't know them. All right, so oftentimes what a lot of students will do is they'll say, oh, well, wait a minute. Okay, we kind of had a similar problem. We were working with confidence intervals. Could we use standard error? Can we replace those p's that we don't know with our p hats, our sample of boys and our sample of girls? Well, that's actually a great idea. It's a fantastic idea. But there's still a problem there. Remember, we need to build this sampling distribution on the assumption that the null is true. And if I'm going to build it on the assumption that the null is true, then why do I even have two samples? Why do I have a proportion of girls? Why do I have a proportion of boys? If I even if I use standard error, I would still be treating them separate. Hey, here's the proportion of girls. Here's the proportion of boys. But the null says that they're equal. It shouldn't be about boys and girls. They're all the same, right? So we actually need to use a very special type of standard error. And that standard error is called the combined standard error. All right. So the idea here is that I can't use the standard error that we used in confidence intervals because that standard error still treats each sample as its own. But remember, the null says that we have to treat these population proportions as equal. So here's how we get what we call the combined standard error. And this is where things get a little bit tricky if you don't pay attention. All right, first, instead of looking at our two samples as two samples, why don't we just combine them all to one giant sample? And I'm going to call that the combined sample. That's what the little c stands for, the combined sample proportion. So my denominator is both samples added together, right? My null is that they're equal, so why not just put them all together? So we have our sample size plus sample size in the denominator. The numerator is my total successes. So if I'm looking at the number of kids that do their homework every night, again, not looking at boys and girls anymore, just looking at kids because they're all the same, right? Then I would just add my total successes on the top. So here is my successes for the boys. That would be the boy sample times the proportion of boys. And the girl sample times the proportion of girls, right? And again, I'm using generic 1 and 2. And again, that's just trying to stay generic. But the point is I need to throw my data together because the null says they're the same anyway. So I'm going to get one combined p hat, call it p hat combined, p hat c. It's a combination of your two samples together. All right, then we're going to use that number back in the standard error formula. And this is what we get called standard error combined. So in the standard error formula, you'll notice that the numerators are the same because there's only one combined proportion. So we're going to use the same value here, and then of course it's opposite, 1 minus it, and then the same number here. Now, there is a potential in a lot of problems where your sample sizes are still different. So I still have to have two separate fractions for my sample size, okay? Even though the numerators are exactly the same, because I'm assuming the proportions are the same, you still might have different sample sizes. So that's why I still have to have the sample sizes separate. So this is the standard error combined. Now the good news is it looks just like our standard error formula. In fact, it looks just like our standard deviation formula. The only difference is the numerator comes from one combined sample proportion that you use for both samples. All right, now, there are two other versions of this formula, but to be honest, I like this one the best because it's easiest to use on a calculator. Because remember, you really don't even need a lot of parentheses. You just type everything in, it gives you the answer. But think about it. The numerators are the same. So if you're good at algebra, you could factor out that common numerator, which leaves behind 1 over n plus 1 over n. And then what you could actually do is use another algebra rule. And there's an algebra rule that says the square root of a times b is the square root of a times the square root of b. So you could then separate these two square roots. Now, some people will say, yeah, this is the formula right here. Okay, any three of these formulas work, guys. All three of these formulas are equivalent. They all are the same thing. I'll be honest. I actually prefer this one on top. A, because it looks like the standard deviation formula that I should be using anyway. And it looks like the standard error formula. The only difference is the numerator. It's using that combined p hat. But you will see these other formulas at use, maybe on a formula sheet, maybe in a textbook. But again, they're all the same form. It's just a matter of doing a little bit of algebra to maybe clean it up. Okay, so now at the end of the day, if we truly understand all that, step 2 is all about checking the conditions and building that sampling distribution on the assumption that the null is true. So once again, what do we need in step 2? We need our 3 conditions in blue, green, and purple. There they are. Same conditions we've been working with for a while. Then we need the mean. What do we expect our difference to be if they're the same? Well, 0. Then we need that standard error combined, which does involve this p hat c, this combined sample proportion. Listen, I've taught this class long enough. I get that seems a little bit weird, but once we get into an actual example in 6.11, it'll actually make a ton of sense, and you'll see how easy it is. It's not that difficult of a thing to deal with. All right. Now that that's over, let's move into step 3. Step 3 is actually pretty easy. It's usually most kids' favorite step. We need a z-score. We need a p-value. So a z-score is actually really simple. We're going to take the difference we did observe. So remember, at the end of the day, we do have 2 samples. We do have a sample from population 1, and we do have a sample from population 2. And remember, yes, the null is that they're the same, but our alternative is we think there's a difference. Whether greater or less than, we think there's a difference. So to find that z-score, you're going to take the observed difference between your 2 samples. Okay, that's your observed difference right here. And then we're going to subtract the mean. Well, remember, the mean is 0. We expect there to be no difference. So to be honest, you don't even have to subtract 0 because it doesn't do anything. But technically, I want to write it there. That way you understand I am subtracting the mean because, the formula for standard deviation does say to subtract the mean. Okay. And then on the denominator, you need the standard error. And again, that's the standard error combined. You need the standard error combined. And that's the formula we just talked about. Okay, so once you get your z-score, you're going to have a value there. You're going to have a number. You're going to have a z-score. If it's negative, we want to look more extreme. So that's even lower. If it's positive, we want to look more extreme. That's even higher. So the p-value is the probability of a sample difference being more extreme than the difference we observed, assuming the null is true. So we're finding the probability that a difference, p hat 1 minus p hat 2, is greater than or less than, if it's negative, the observed difference. Now, again, that observed difference is going to come from your sample. So I can't give you a number there. It's going to be an observed difference, right? Once you see an exact example in the next video, you'll understand that. And then that's equal to the probability that a z-score is greater than our z-score that we got, whatever z-score that was. And then again, of course, to find the actual probability, the p-value, we're going to go ahead and use normal CDF. So again, key thing is that you understand what a p-value is. It's the probability of a sample difference being more extreme than the difference that we observed, comma, assuming the null is true. All right, once you have that p-value, it's all about making a conclusion. So we always need, we're always looking for evidence to confirm the alternative hypothesis. Otherwise, we do not have evidence to confirm the alternative hypothesis. We never have a conclusion that's about the null. We never say, oh, the null's wrong, the null's right, the null's true, that we confirm the null, we have proven the null. No, it's all about the alternative. So to make this decision, we're going to use our p-value. If our p-value is less than our significance level, meaning that that p-value is very significant, our sample is very significant, assuming the null is true, then we will reject the null. So, all right, so if we have a p-value that's less than our level of significance, we'll reject the null. And in context, this means that we do have significant evidence that the alternative is true. So if the teacher could get a very low p-value, 0.00000001, then that teacher can officially say, listen, I do have significant evidence that the proportion of boys that do their homework every night is less than the proportion of girls. All right, if the p-value is high, more than our significance level, so if you have a significance level of 0.05, anything above that is not significant. In this case, we would fail to reject the null, which means we do not have significant evidence that the alternative hypothesis is true. Notice that we don't say, oh, we have evidence that the null is true. No, it's never about the null. It's all about the alternative. So if I fail to reject, let's just say that, the economist gets a p-value of 0.09. Well, then the economist is going to say, I fail to reject the null. I do not have evidence that the proportion of unemployed adults in America is greater than the proportion of unemployed adults in Canada. Now, maybe he still in his heart believes that to be true. He just doesn't have the evidence to support that. And that's how you make a conclusion. All right, so at the end of the day, these 4 steps should sound very familiar. The whole process is exactly the same as it has been in the past. The only real change is kind of getting that standard error combined. It's kind of a little bit weird, but it'll actually be really simple once you see a video for how to actually do it, which you'll see in 6.11. All right, good luck. Hope you understand it all. Watch it again if you need to. See you later.